Okay, so the change in enthalpy is a concept that involves whether a chemical reaction is exothermic, which is indicated by a negative delta H sign, or endothermic, which is indicated by a positive delta H. And a direct method to calculate delta H, usually on a test, is when they give you the bond energies, the sum of the bond energies in the reactants minus the bond energies in the products, because delta H represents the energy required to break the bonds minus the energies released when forming the products. So that's why it's reactants minus products. And this is a more direct method. How delta G, delta H, and delta S are related is that the Gibbs free energy, which determines the spontaneity or non-spontaneity of a reaction, so whether a reaction will just happen instantly without outside interference, is determined by delta H, which is the change in enthalpy, minus the temperature in Kelvin, which will always be positive. Note that, times the change in entropy. And the change in entropy is actually entropy itself is a measure of a disorder. So actually the products of a reaction have become more disorderly or less disorderly. And delta S can be represented as, for example, a reaction where water boils. So this would be an example of a reaction that has a positive entropy, since it is becoming more disorderly. More disorderly means the molecules in this substance are becoming more spread out, and as if a pile of bricks fell off the back of a moving truck, then it would naturally become disorderly. It would fall in ways, increasing in entropy. More disorder. And or non-spontaneous, depending on its exothermic or endothermicness, or its entropy, change in entropy. We're going to change this so this is our dependent variable. Dependent variable means it changes in response to the independent, which is the H and the S, but let's focus on the S first. So if we have a positive H, that means we have, let's just make this positive 1 to make it easy. So positive 1, the T positive, because it's S, T times a positive number, which would make it positive. This would be ambiguous because, for example, if the temperature were high enough, in this case, let's think of an example of a reaction that has positive delta H and positive delta S, which is an ice cube melting. An ice cube melting turns from a solid to liquid. Solid to liquid means the entropy is increasing. The change in entropy is positive, and delta H is positive because it's endothermic. Endothermic means the heat is flowing from the surroundings to the system, and system in our case is the ice cube, and the surroundings is these surrounding air. And when delta G is positive or negative, it can be positive or negative. The reason why it's positive or negative is because it depends on temperature, as I said here, T. And delta H can also be determined indirectly by Hess's law. So in addition to this method, you can also do it by this method. So when you're given the delta H's of 3 reactions, you can find the delta H of another reaction implicitly or indirectly by summing up all the successive delta H's in a specific order that yields the things you want on one side and the things you want on this side. So what we want is this, and this. So we have SO2 here, H2O here, 3O2s, they are both over here. So we're not going to target one equation particular, which means we're going to deal with this last. This is least important. HS, H2S, we have it right here. So let's get to our 2SO2. So when we want 2SO2, we have to multiply each by 2. So we're just going to have to multiply everything by 2 to get this. And since you multiply everything by 2, you would also have to make the delta H also be multiplied by 2. This times 2, which is negative 593.6. And we want 2 waters, so we'll have to multiply everything by 2. Now we need to, so we have our water and our sulfur dioxide. Now we want in our final, we want H2S because these two adding up already equals 3O2, so we have this handy. Now we want dihydrogen sulfide. So in this case, since we want the dihydrogen sulfide on the reactant side for here, we're going to multiply, and we want 2 of these two, we're going to multiply everything by negative 2. So multiply this delta H by negative 2 as well. So keep that in mind. So negative 2 times, the negative 2 is the same as just reversing the reaction and multiplying everything by 2 at the same time. So it would be, we're going to put this in our reactants this time. Our new delta H would then be negative 2 times 20.6, negative 20.6, positive 41.2. I'm going to leave out the positive sign because we can assume it's positive. Now let's sum all the things we have now. So everything here is going to go on the left, everything here is going to go on the right, because I would run out of space. So when we add everything up, let's cancel out stuff that we see. So spectator substances, I would call them. So we see 1 sulfur on this side, we see 2 sulfurs on this side, and also 2 sulfurs on this side. So let's cross these out. We have what we want. Let's actually look at what we want. So we have this. It's check. Let's look at the H2S. We have this H2 cancel out the 2H2 here, and we have what we want here. So check mark, and we have what here. So the total reaction would be, finally have our products that we want. So we have our dihydrogen sulfide and oxygen gas, and we also have our liquid water and just water and sulfur dioxide. And in the end, we also add up the delta H's we have to find our total enthalpy, the total change in enthalpy which we wanted to find in the first place.